Our next step now is to ask what happens if we don't have a circuit with just series or just parallel? Can we still get an equivalent resistance and how do we deal with it? We certainly can still get an equivalent resistance, but what you have to do is work step by step and draw pictures as you go. So what you do is you look at your picture and you ask, do I have any obvious connections, one that really jump out at me as being a connection? So when I look at this picture here, if I look at the 90 and the 45 ohm resistor, I see that those are in parallel connection because the two tops are connected and the two bottoms are connected. So that's a parallel connection, which means I can draw an equivalent circuit where I take out the 90 and the 45 and I put in an equivalent resistance. So this one is going to be my 10 ohms. Still got my 25 on the other side. And now I have to calculate what is that equivalent resistance. I'll use my equation. 1 over R equivalent equals 1 over R1, which is 90 ohms, plus 1 over 45 ohms, or 1 over R2. So 1 over 90 plus 1 over 45. 1 over 45 is the same as 2 over 90. So 1 over 90 plus 2 over 90 is 3 over 90 ohms. Again, if you're more of a digits kind of person, you might just straight up do that in your calculator, which is absolutely fine. I'm a bit more of a fractions person, so I tend to do it that way. So I've got 90 ohms divided by 3, or 30 ohms. Okay, I'm going to fill that in on my picture. Okay, next I look, what is my next obvious connection? What is really leaping out at me? Well, if I look at that 10 and that 30, those are a series connection because they're all in a line. So I go right from the 10 to the 30. I can draw a new equivalent circuit where I've still got my 25 ohms on the right. But now on the left, I have the series equivalent of the 10 and the 30 together. As a refresher, to get your series equivalent, you just straight up add them. So R1, which is 10 ohms, plus R2, which is 30 ohms, to get the equivalent resistance of 40 ohms. And I'll label that on my diagram, 40 ohms. Now I'm down to two resistors. They have a connection. The connection they have is that they are connected at their tops and they are connected at the bottoms. Those two are a parallel combination. So I'll do my last equivalence by adding those guys in parallel, and I will draw a new diagram where I'm left with one single resistor. So 1 over R equivalent is 1 over R1, which is 1 over 40, plus 1 over 25. I can use a lowest common denominator of 200, so that gives me 13 over 200 ohms. My R equivalent is 200 ohms over 13, which is 15.4 ohms. So that's how you do equivalent circuits. So you just work on them step by step and figure out what's in series and what's in parallel. We're going to do some more analysis on this circuit. Just before we get started, the things to keep in mind is that our equivalent circuit will have the same potential. Okay, so I'm drawing two purple stars on the left diagram. Going to have exactly the same potential between the two purple stars on the left and on the far right. We're also going to have the net current down on the far left is going to be the same as the net current down on the far right. So it's an equivalent circuit, so our equivalent resistance draws the same current when there's the same potential. So we're going to keep those things in mind and we're going to move on with our analysis. Our question now is telling us that if the potential difference across the top and the bottom of the circuit, so between here to here, I'm going to draw this over on the side, so from there to there is 12 volts. Find the current through each resistor. Let's just think about what happens. Some current comes in through the top, it hits this junction, some of the current splits down here, some of it splits over here. For the current that goes through the 10 ohm resistor, it hits a junction. It's going to split so that some of it goes through the 45 and some of it goes through the 90. After it comes through the 90 and it comes through the 45, it's going to recombine and come out through right here. Just like the current that comes out from the 25 passes through the 90 and the 45 and comes out, recombines here and goes back out through the circuit. So that's what's happening with our current. What we're going to do now is we're going to compare our original circuit to our equivalent circuit and all those intermediate steps. We're going to apply Ohm's law to each of those steps. We're going to remember that things in parallel have the same potential, things in series have the same current, and we're going to work through each of those diagrams and ultimately find the current through each resistor. Let's keep going with our problem. What I've added to the slide here now is all of those intermediate diagrams that we used as we were finding the equivalent resistance. So each of these four circuits have the same potential across the 2 points, so 12 volts across top and bottom, and they have the same net amount of current delivered. So let's work through them step by step. We're going to use Ohm's law, and we're more or less going to work backwards. So Ohm's law is V equals IR, and work backwards. So let's make a note of our strategy before we get going. By work backwards, I mean we're going to start at the equivalent circuit, so our diagram on the far right, with the potential of 15.4 ohms. We're going to work on that circuit, and then we're going to work our way back towards the left. So we'll start at the rightmost diagram, see what we can figure out there, and we'll label things as we go, and we'll learn step by step. So on our rightmost diagram, we know that the potential across our 2 points is 12 volts. That tells us that the potential difference across the 15.4 equivalent resistance is 12 volts. If we know the potential, and we know the resistance, then we can find the current, because the current is going to be the potential divided by the resistance. So 12 volts over 15.4 ohms to get 0.78 amps. So our current through this equivalent circuit is 0.78 amps. 0.78 goes in, 0.78 goes through the resistor, and 0.78 comes out. Let's label this in each of the other pictures where it belongs. So 0.78 comes in. We could label that it comes out too, but I think I won't bother messing up my diagrams like that right now. Let's see what else we know. When we found our 15.4 ohm equivalent resistance, we found that by doing the parallel combination of the 40 and the 25. Remember, things in parallel have the same potential. So if the 15.4 ohm equivalent resistance has a potential of 12 volts, then my 25 ohm resistor has a potential of 12 volts, and my 40 ohm resistor has a potential of 12 volts. Because the 40 and the 25 are in parallel, they have to be the same potential, and they have the same potential as that parallel equivalent. Okay, so now we're going to work with our blue diagram. We know that a current of 0.78 amps comes in. Some of it splits down and goes through the 25, and some of it goes through the 40. We know the two resistances, we know the two potentials. We can find those two currents. So for the 25 ohm resistor, the current through it is the potential across it divided by the resistance, 12 volts over 25 ohms. So the current through my 25 ohm resistor is 0.48 amps. I'm going to put that on my diagram. And through my 40 ohm resistor, My current is my potential divided by my resistance. 12 volts divided by 40 ohms gives us a current through that resistor of 0.30 amps. And I'm working in 2 sig figs here just because I don't have a whole lot of room on the slide. If you prefer to work with 3, that's absolutely fine, of course. Okay, now remember, our goal is to find the current through every resistor. So I have currently found the current through the 25 ohm resistor. I'm going to add that on my leftmost diagram because that's what we're trying to find. 0.48 amps. Okay, that one's done. Now, let's back up another step. When we found our 40 ohm resistor, we found that by doing the series equivalent of the 10 and the 30 ohm resistor. Things that are in series have the same current. So our 25 ohm resistor, remember, had a potential of 12 volts and it had a current of 0.48 amps. Our 10 ohm and our 30 ohm, they got added together to give us 50 ohms, or 40 ohms, sorry, and the current through that 40 ohms was 0.3 amps. Because the 10 and the 30 are in series to give the 40, the 10 and the 30 have the same current as each other, and they have the same current as that 40. So there's 0.3 amps through the 10 ohm resistor, and there's 0.3 amps through the 30 ohm resistor. Okay, now we've got another one of our resistors done. The 10 ohm resistor has a current through it of 0.3 amps. So let's see, what else can we find? If we look at our 30 ohm resistor, we see that it has a current through it of 0.3 amps. We could find the potential across that resistor. So for our 30 ohm resistor, the potential across it is the current through it times the resistance, 0.3 amps times 30 ohms, to give us a potential of 9 volts. So our 30 ohm resistor has a current of 0.3 amps and a potential of 9 volts. And if you were asked to, you could find that the potential across the 10 ohm resistor were 3 volts to give you a total there on that branch of 12 volts. We weren't asked for that part, so we don't have to do that. And I think for the sake of not getting too cluttered, we won't write that down. Okay, let's think about our 30 ohm resistor a little bit more. We know it's got a current of 0.3 amps. We know it's got a potential of 9 volts. So let's think about where that 30 ohm resistor came from. The 30 ohm resistor was a parallel combination of our 90 ohm resistor and our 45 ohm resistor. Since it's a parallel combination, then the 90 ohm resistor and the 45 ohm resistor, they have the same potential as each other and of the parallel equivalent of 30 ohms. So they have a potential of 9 volts. If we want to find the current through both of those resistors, then we'll use Ohm's law and we'll solve for current. Let's do the 45 ohm resistor first. So current is going to be potential divided by resistance, 9 volts, divided by 45 ohms to get 0.20 amps. Let's label that in, 0.20 amps. And then for our 90 ohm resistor, current is potential over resistance, 9 volts over 90 ohms equals 0.10 amps. Let's fill that in on our diagram. Okay, now we've found the current through every resistor. So you might notice here that your 0.78 coming in splits to 0.48 on the right, 0.3 on the left to sum up to 0.78. Of your 0.3 on the left, it splits to 0.2 on the right and 0.1 on the left, so it splits over the 2 branches. You see that the things with the higher resistances get less current because it's harder to go through, and the things with lower resistance get more current. So these problems where you have to do equivalent circuits and you have to figure out the potentials and the currents, they're not difficult, but you do need to stay really organized and try not to get all scrambled up in the middle. So you just follow the process step by step. You look at every single resistor. You ask, what was the connection and what do I know? And that should help you figure everything out.